Supernovae are not just amazing events in the universe. They're vital cosmic phenomena that shape and create galaxies. These powerful explosions occur at the end of a massive star's life cycle, ejecting elements into space from which new stars, planets, and even life itself are formed. In essence, supernovae serve as both destroyers and creators of galaxies. In the study of supernovae, imagery plays a crucial role in understanding these powerful explosions. Over the years, advances in imaging technology have allowed astronomers to capture spectacular views of supernovae at different stages, revealing intricate details of their structure and the elements they eject into space. The story of Betelgeuse, a red supergiant star, is a prime example of how images help us understand the behavior of supernovae. Betelgeuse has recently attracted a lot of attention due to its sudden fades and increases in brightness. This variability has led to speculation of its imminent explosion, sparking widespread interest. The appearance of a dust cloud around the star, observed in telescopes and captured on images, was initially taken as a precursor to a supernova. However, later it began to be considered as a natural phenomena in the life cycle of red supergiants. So why did scientists initially hypothesize the possibility that this star would be the next observed supernova? This red supergiant occupies a prominent place in the constellation of Orion, perched on its shoulder, and is visible to the observer even to the naked eye. Let's take a look at the life cycle of Betelgeuse, an intriguing journey that will show the evolution of the star from its birth to its current state as a massive, pulsating giant nearing the end of its life. Betelgeuse began its existence as a massive star burning hydrogen in its core, like many others. However, because of its large mass, it evolved rapidly, entering successive phases of nuclear fusion. The significant mass of the star distinguished its evolutionary path from the evolution of smaller stars, such as our Sun. While the Sun is currently a stable main-sequence star slowly converting hydrogen into helium, Betelgeuse, due to its much larger mass, more quickly depleted its hydrogen reserves and evolved into a red supergiant. The key difference between Betelgeuse and our Sun is their masses. Betelgeuse, which has about 15 to 20 times the mass of the Sun, experiences higher pressure and temperature in its core, which accelerates nuclear fusion. Intense fusion causes Betelgeuse to burn its fuel rapidly, resulting in an unstable structure and significant brightness fluctuations. In contrast, the Sun's lower mass allows it to remain stable for billions of years, with a much longer and more stable hydrogen burning phase. As Betelgeuse aged, it entered successive phases of nuclear fusion, gradually burning off elements heavier than hydrogen. Internal pressure caused the star to begin to swell, transforming it from a main-sequence star into a red supergiant. This stage is characterized by Betelgeuse's enormous size and variability in brightness. The star expands and contracts as it undergoes complex nuclear processes. Recent observations have suggested that Betelgeuse may be on the verge of a supernova. The star's dimming in 2019, followed by an unexpected increase in brightness, has led scientists to speculate that it may be approaching the final stage of its life. These changes in brightness are thought to be related to internal processes, possibly signaling the beginning of core collapse. The star's pulsations, with cycles of 185, 230, 420, and 2200 days, were analyzed to understand its internal dynamics. The longest cycle of 2200 days is particularly intriguing because it may represent Betelgeuse's fundamental pulsation mode, indicating its advanced stage of evolution. These observations, along with recent telescopic findings, suggest that Betelgeuse may be entering a phase of carbon combustion that precedes a supernova explosion. But what are the complex nuclear processes that dictate when a star's life must come to an end? At the center of a massive star like Betelgeuse, nuclear fusion turns hydrogen into helium, releasing enormous energy. As the star ages, heavier and heavier elements fuse to form bulb-like layers. Eventually, the core is filled with iron, which cannot release energy during the fusion process, leading to gravitational collapse. As the core collapses, a runaway reaction is triggered. In this process, the iron core collapses under enormous gravitational forces, reaching temperatures of billions of degrees. This leads to the rebound effect, where the core inflates and then explodes, creating a shockwave that rips the star apart. A supernova explosion releases an enormous amount of energy, briefly eclipsing an entire galaxy. The mechanics of this process involve a complex interplay between nuclear collapse, gravitational forces, and intense heating. The shockwave generated by the collapse of the core propagates outward, ejecting the outer layers of the star into space. Ancient astronomers have recorded these bright phenomena for thousands of years, sometimes describing them as guest stars or new stars. The earliest recorded supernova observation dates back to 185 AD when Chinese astronomers observed guest stars, as they called them, that were visible for 8 months. Although rare, astronomers continue to study them to this day, especially when they lead to unusual phenomena such as gamma-ray bursts. Gamma-ray bursts, or GRBs, are intense bursts of gamma rays, usually associated with the collapse of massive stars or the merger of neutron stars. These bursts are some of the most energetic events in the universe, capable of releasing more energy in just a few seconds than the Sun will emit in its entire 10 billion-year lifetime. The discovery of the Boat GRB, also referred to as the brightest of all time, in October 2022, was a milestone in GRB observations, stunning astronomers with its unprecedented brightness and startling impact on Earth. The Boat GRB, officially designated GRB 221009A, was detected on October 9, 2022, and originated from a galaxy about 2.4 billion light-years away from Earth. The event was unusual not only in its brightness, but also in its duration. It lasted about 7 minutes, much longer than a typical gamma-ray burst. The burst was so powerful that it affected the Earth's ionosphere, temporarily disrupting radio communications and altering the ionization of the atmosphere. The relationship between supernovae and gamma-ray bursts is complex and fascinating. In some cases, the collapse of the core of a massive star can trigger a GRB, especially if the star is rapidly rotating and has a strong magnetic field. Such long GRBs often last more than 2 seconds and are often followed by a supernova explosion. Boat was notable not only for its brightness but also for providing insight into the formation of heavy elements. In April of this year, scientists studied this burst in detail, initially hoping that it might provide clues about the origin of elements heavier than iron, which are usually formed in supernova explosions or neutron star mergers. However, further analysis showed that GRBs do not produce these elements, leaving scientists even more puzzled and emphasizing the mysterious nature of such cosmic phenomena. To find out exactly what caused the flare, scientists used a variety of observational tools, including the James Webb Space Telescope. The exceptional brightness of the flare initially obscured its surroundings, making it difficult to observe the accompanying supernova or other objects in the host galaxy. It took several months before the brightness diminished enough to make detailed observations possible. As a result, a relatively undetectable supernova remnant was detected, which was surprising given the power of the gamma-ray burst. The boat GRB also provided insight into the characteristics of gamma-ray bursts. The exceptional brightness and long duration of this event indicated that the GRB was very focused, with narrow jets pointing directly toward Earth. This narrow directivity likely contributed to the observed intense brightness, as gamma-ray bursts tend to be directional phenomena. The narrow burst jets were probably the result of a rapidly rotating star with a strong magnetic field that produced a powerful and focused flare. While both GRB has provided insight into gamma-ray bursts and supernovae, scientists continue to find answers to the mysteries of Betelgeuse. Recent research suggests that Betelgeuse's cycles of dimness and brightness are part of its natural behavior as a variable star. It turns out that, unlike our Sun, Betelgeuse is an extremely explosive and low-density plasma cloud that changes shape frequently. Created by scientists, simulation illustrates the behavior of Betelgeuse in time. Periods of brightness and dimness occur about every 400 days, and the longer cycle is about 2,000 days. Recent studies have tried to explain the Great Dimming phenomena that occurred in 2020, and observations from various telescopes over the past 15 years have provided much insight. Observations at various frequencies, including microwaves and infrared, have allowed scientists to penetrate the layers of Betelgeuse and detect silicon monoxide, indicating the presence of a large dust cloud. This discovery disproved initial speculation that Betelgeuse was about to explode. Instead, it appears that internal activity within the star has caused the material to separate, forming a large gas cloud. The formation of a cold region beneath this cloud caused particles to condense, creating a dark cloud that obscured Betelgeuse from view from Earth. Further study of Betelgeuse's behavior revealed that the star experienced two shockwaves, one in 2018 and another 1 year later. These waves disrupted the surface, creating hot and cold spots, which was confirmed by Hubble Space Telescope ultraviolet imaging observations. The shock waves and their aftermath disproved the initial assumption that Betelgeuse was close to a supernova, and instead showed that this behavior of the star is part of its natural life cycle. Betelgeuse's behavior is also characterized by its high rotation rate. Unlike typical red supergiants, which rotate slowly, Betelgeuse rotates at about 3 miles per second, which initially led researchers to think that it might have been a binary star that collided. However, recent research suggests that this rotational speed may be influenced by fast-moving convective cells inside the star, contradicting initial assumptions about its rotational behavior. Despite the unusual behavior, this research suggests that Betelgeuse is unlikely to become a supernova in our lifetime. The current state of the star is more like a variable red supergiant nearing the end of its life, but by no means approaching a supernova explosion. So finally we come to the very question that concerns all of us. How would such an explosion affect our home planet? The potential impact of a nearby supernova on Earth is a subject of speculation and concern. While a supernova is not expected to pose an immediate threat to our home, the explosion of a star within a few light years could affect Earth's atmosphere and potentially impact life. For example, the flare of the very same boat GRB was so intense that it significantly affected the Earth's ionosphere, altering atmospheric conditions and disrupting radio communications. The flash released a tremendous amount of energy that interacted with the Earth's atmosphere, causing a sudden increase in ionization. This increased ionization affected the ozone layer and triggered chemical reactions that scientists are still trying to understand. The GRB also disrupted radio signals, especially those used for communication and navigation. The energy released in the explosion was so great that it even blinded several satellites, demonstrating the enormous power of these cosmic phenomena. However, the burst itself was observed from a galaxy a whopping 2.4 billion light-years away. This event only emphasizes the need for further study of gamma-ray bursts to understand their impact on us, our planet, and the universe as a whole. In addition, supernova studies also contribute to our understanding of dark matter, dark energy, and the overall structure of the universe. Type 1a supernovae, which occur in binary star systems, are crucial for measuring cosmic distances and studying the expansion of the universe. These standard candles have helped astronomers detect the accelerating expansion of the universe, which in turn has provided the background for understanding dark energy. Supernovae are a key focus of future astronomy. Their explosive nature and transformative impact continues to fascinate scientists and inspire discovery. Well, while some people are frozen in anticipation of the Betelgeuse explosion on live internet feeds, we look forward to discoveries from missions such as the Vera Rubin Observatory and the European Space Agency's Euclid telescope, which will contribute to advancing our understanding of supernovae. As we look deeper into space, these stellar explosions will undoubtedly shape our understanding of the universe and our place in it. Surely you've heard by now that black holes can be so massive that they can outshine entire galaxies? But some of them are quite mobile. So much so that they roam the Milky Way like cosmic ghosts, undetectable. Of course, you may be confused or even mesmerized by the fact that the nearest black hole to Earth is not as far away as you think. And when these cosmic giants collide, they generate frequencies as unique as fingerprints. Frequencies that may hold the key to unlocking the deepest mysteries of the universe. But did you know that these waves interact in a far more complex way than we ever imagined? Get ready for an extraordinary journey as we begin to delve into the mysteries of black holes, the truly enigmatic titans of the universe. In the cosmic pattern, black holes are weavers of riddles and paradoxes. Although we're familiar with small black holes, the remnants of dying stars and supermassive ones lurking in the hearts of galaxies, there is an enigmatic class that eludes our telescopic gaze: intermediate mass black holes. The Hubble Space Telescope, our eye in the sky, recently focused its attention on Messier 4, the ball cluster closest to Earth. What he discovered was nothing short of groundbreaking: a black hole with a mass about 800 times the mass of our Sun. This celestial object is somewhere between 6,000 and 7,200 light-years away from us. Why is this so important, you ask? Well, for years, astronomers have struggled with a gap in the black hole genealogical tree. We've had evidence of both small black holes, a few times the mass of our Sun, and supermassive black holes with masses in the millions or billions of solar masses. But black holes of intermediate mass turned out to be a missing link, mysterious relatives about which everyone has heard but no one has met. An equally interesting question is how these black holes of intermediate mass form. One theory suggests that they could be the nuclei of dwarf galaxies that lost their outer stars when they merged into larger galaxies. Another theory states that they could have formed from the collision and merger of smaller black holes. Identifying these elusive black holes is no easy task. It requires a symphony of scientific instruments, from X-ray observatories to precise calculations based on the motion of surrounding stars. The Hubble Space Telescope, with its unprecedented resolution, has played an important role in this discovery. The presence of a black hole affects its cosmic environment. By studying the gravitational choreography of stars orbiting this massive object, scientists have been able to estimate its mass. It's like understanding the character of an invisible puppeteer by watching the puppets dance. The discovery of intermediate mass black holes could rewrite the cosmic narrative. They may be key players in the formation of galaxies and may even hold clues to the mysterious dark matter that makes up most of the universe. In a cosmic world where distances are often incomprehensible, the term neighbor takes on new meaning. While our closest celestial neighbor, the Moon, is only 238,855 miles away, our nearest neighboring black hole, Gaia BH1, is thousands of light years away from Earth. But what does that proximity mean in the context of black holes? And why is this proximity important? In 2020, the European Southern Observatory, ESO, made headlines when it announced the discovery of a black hole in the HR 6819 system, located just 1,000 light-years away. This would make it the closest known black hole to Earth. However, this claim was later disproved. Subsequent research by Abigail Frost of the University of Leuven in Belgium found that HR 6819 does not contain a black hole at all. Instead, it's a double star system in which one star absorbs the mass of the other, a process known as stellar vampirism. This revelation was more than just a correction. It opened up new possibilities for studying stellar evolution and interactions. After the ejection of HR 6819, the title of the closest black hole to Earth went to Gaia BH1. This black hole was discovered by the Gaia Space Observatory, a mission of the European Space Agency, ESA. The main task of Gaia is to map the Milky Way in unprecedented detail, and it was thanks to this painstaking work that Gaia BH1 was discovered. As the closest known black hole to Earth, Gaia BH1 offers a unique opportunity for scientific observations and research. Its relative proximity allows for more detailed measurements and may help answer fundamental questions about the properties of black holes, such as mass, rotation, and behavior near their event horizons. The study of black holes like Gaia BH1 relies on several observational instruments, from X-ray observatories to radio telescopes. Each instrument represents a piece of the puzzle. The closer a black hole is, the more accurately these instruments will be able to measure its properties, offering a more complete picture of these mysterious objects. Beyond its scientific significance, the idea of a nearby black hole captivates the public imagination. It makes the cosmic more personal and provides a tangible focus for education and outreach. The story of Gaia BH1 can serve as a gateway for people to astronomy and astrophysics, enriching our collective understanding of the universe. In the cosmic theater, black holes often play the role of mysterious villains lurking in the centers of galaxies or double star systems. But what happens when a black hole is left to roam the universe alone, unconnected to any galaxy or star? What causes these black holes to become rogue? And how do astronomers even manage to find such elusive objects? Let's dive into the mysterious world of rogue black holes. The scientific community was ecstatic when astronomers announced the first ever unambiguous discovery of a wandering black hole. Located 5,000 light-years away from Earth, this black hole weighs 7.1 times the mass of our Sun and moves at a staggering speed of about 28 miles per second. The key to this revolutionary discovery lies in a phenomena predicted by Einstein's general theory of relativity, known as gravitational lensing. When a massive object, such as a black hole, passes in front of a background star, its intense gravitational field deflects the light of that star. This creates a brief brightening phenomena, which is how this wandering black hole was discovered. As we know, the birth of a wandering black hole is nothing short of a dramatic event. When a massive star exhausts its nuclear fuel, its core collapses, leading to a supernova explosion. The energy released can be so enormous that it ejects the newborn black hole from its stellar cradle, sending it on an endless journey through space. And this is how our newly discovered wandering black hole likely began its cosmic odyssey. What is even more intriguing is the speed at which this wandering black hole is traveling. Its speed is about 28 miles per second, which is a very large value relative to the nearest stars. This speed is likely the result of the very impact of a dying massive star, sending it on a lonely journey. The discovery of this lone black hole is just the tip of the iceberg. In upcoming missions, such as the European Space Agency's Gaia telescope and NASA's Nancy Grace Roman Space Telescope, astronomers expect to find even more such space travelers. These future discoveries will not only increase the number of known rogue black holes, but also refine our theories about their properties and frequencies. Each galaxy is like a cosmic dance floor, where stars, gas, and dust swirl in a complex choreography. At the center of this dance is a supermassive black hole that sets the rhythm and tempo of the entire galaxy. Research published in the monthly notices of the Royal Astronomical Society shows that galaxies and their central black holes grow together, regardless of their location in the universe. Astronomers have long been puzzled over the relationship between the mass of a galaxy and its central black hole. The two seem to be aware of each other even though the black hole is much smaller than the galaxy in which it resides. This relationship implies a deep cosmic connection, a kind of cosmic codependency where the growth of one affects the other. One of the most intriguing questions in astronomy is, which came first, the galaxy or its central black hole? The answer remains elusive. What is clear, however, is that a close connection was established very quickly on a cosmic scale, paving the way for a complex interplay of growth and evolution. Let's dive into the young, gas-rich galaxies, the cradle of giant black holes. These galaxies are like cosmic nurseries, teeming with the raw materials needed for star formation and black hole growth. Studies show that such galaxies, known as blue nuggets, have exceptionally high star formation rates. They are fed by nearby gas streams, which not only accelerate star formation, but also contribute to the rapid growth of their central black holes. When black holes are fed, they become active. The gas around them heats up and emits powerful waves of radiation. This heated gas is less likely to hit the black hole, creating a feedback loop that stabilizes the size of the black hole. However, as the galaxy grows, it can push more gas toward the center, allowing the black hole to feed and grow again. The relationship between galaxies and their black holes adjusts itself. If a black hole is too large for its galaxy, it grows slower, and if it's too small, it catches up due to the abundance of gas and dust in the galaxy. So some galaxies defy the norm. These blue nuggets, despite their small size, have exceptionally large central black holes. As these galaxies age, their star formation stops, and they turn into red nuggets, still retaining their huge black holes. As we move farther into the black hole abyss, it becomes apparent that young, gas-rich galaxies serve as the birthplace of various black hole phenomena. Whether they're luminous black holes or intermediate mass, wandering black holes hurtling through space, or the nearest black holes to Earth, their origins can often be traced back to these bright, young galaxies. Understanding the cradle of these cosmic giants helps us unlock the mysteries that black holes hold. Now, let's look at something really rare. There is a situation where black holes collide. In doing so, they create a cosmic symphony of gravitational waves around them that vibrate in the very fabric of space-time. These waves, first detected by the Laser Interferometer Gravitational Wave Observatory, in 2015 opened a new frontier in astronomy. However, recent research shows that these waves interact in complex ways as they propagate, thereby testing our understanding of gravity and the general theory of relativity. Traditionally, scientists have used linear models to describe these waves. However, a new study has revealed nonlinear effects that reveal a more complex picture. It's akin to the difference between a calm pond and a rough sea. In a calm pond or linear pond, the throw of a stone creates an isolated ripple. In a stormy sea or nonlinear, however, multiple forces interact to create complex wave patterns. When black holes collide, they emit unique frequencies or chirps. These sounds are like individual notes in our cosmic symphony, each telling us something about the properties of colliding black holes. They offer a new way to test the limits of the general theory of relativity and may even provide clues to the nature of dark matter. Recent discoveries have shown that pairs of black holes and dwarf galaxies are on a collision course. These dwarf galaxies attract gas that feeds their black holes, causing them to grow even before they merge. This process is a microcosm of the larger universe, where galaxies and their central black holes grow in tandem. These colliding dwarf galaxies offer a glimpse into the early universe, which was filled with similar small galaxies. Most of these eventually merge to form larger galaxies, like our Milky Way. Understanding these processes helps us piece together the cosmic mystery of galaxy and black hole formation. As we travel deeper into the abyss of black holes, we discover that each type, from luminous black holes of intermediate mass to wandering black holes hurtling through space, plays a unique role in this great cosmic symphony. The next generation of gravitational wave detectors will likely deepen our understanding of these cosmic phenomena. And of course, each discovery, from the frequencies they generate to the nature of gravity itself, undoubtedly adds a new level to our understanding of the universe. As our telescopic eyes become sharper and computational models become more sophisticated, who knows what other cosmic mysteries these giants of the cosmos will reveal. There's an interesting mystery in our world, generated by the equations of Einstein's general theory of relativity. It's the theoretical analog of the black hole familiar to many. We call it a white hole. Imagine a region of space where, unlike an all-consuming black hole, nothing can penetrate. Instead, this cosmic anomaly defies our expectations by ejecting matter and energy, glowing violently on the dark canvas of space. In a universe governed by the concept of an arrow of time, where events flow from past to future, a white hole is a tantalizing paradox. It's like watching a space movie in reverse, where the rules of gravity and time seem to be rewritten. But are these celestial wonders just mathematical curiosities? Or do they hold the key to understanding the deeper truths of our universe? Let us delve into the mysteries of white holes, exploring their theoretical underpinnings, their enigmatic characteristics, and their potential role in the great history of the universe. In the early 20th century, Albert Einstein revolutionized our understanding of the universe by creating the general theory of relativity. This groundbreaking theory proposed a radical idea. Gravity is not a force pulling objects together, but rather a curvature of space-time caused by mass and energy. Imagine space-time as a fabric stretched like a cosmic trampoline. When an object of mass, such as a star or planet, lands on this fabric, it causes a dip. This curvature directs the motion of other objects, which move along curved trajectories in space-time. This is gravity, as Einstein envisioned it. Einstein's theory led to the prediction of black holes, regions in space where the gravitational pull is so strong that nothing, not even light, can escape. These cosmic giants form when massive stars collapse under their gravity. distorting space-time to the extreme. Introducing Carl Schwarzschild, a brilliant physicist who, while fighting in World War I, found an interesting solution to Einstein's equations. Schwarzschild's solution described space-time around a spherical, non-rotating mass, such as a star. Schwarzschild's work laid the foundation for understanding black holes, but it also hinted at something even more mysterious. If a black hole is a region from which nothing can escape, could its polar opposite exist? A region where nothing can enter but only leave. This led to the birth of the concept of a white hole. Just as a black hole is the end point of gravitational collapse, a white hole can be thought of as a reverse black hole, a cosmic fountain ejecting matter and energy. However, unlike black holes, which have already been observed, white holes remain a theoretical concept, a tantalizing possibility in the vast cosmic mystery. In the field of astrophysics, the path from mathematical abstraction to physical reality is often long and difficult, and white holes are no exception. These theoretical entities arise from the complex equations of the general theory of relativity, the same mathematical structure that predicts the existence of black holes. The math of white holes is robust, but it's like a jigsaw puzzle with missing pieces. We understand their theoretical basis, but the real challenge is to relate these mathematical models to observable phenomena. Imagine a universe in which, instead of collapsing inward, a region of space-time does the opposite. It explosively ejects matter and energy. This is the essence of a white hole, a mirror image of a black hole, in which the flow of time and matter is reversed. But can these mathematical abstractions exist in our physical reality? The debate among scientists is ongoing and multifaceted. Some theorists suggest that white holes may be remnants of the early universe, exotic structures woven into the fabric of space-time itself. Others suggest they may represent the other end of a black hole, a kind of cosmic exit door from which matter and energy reappear after being swallowed up by the black hole. The novel idea of quantum gravity suggests that as a black hole evaporates over many epochs, losing mass, it may reach a point at which it can no longer sustain itself as a black hole. At that point, it may turn into a white hole, releasing the trapped contents back into the universe. However, there are serious problems with the physical existence of white holes. The laws of thermodynamics, especially the concept of entropy, presents a serious obstacle. Entropy, a measure of disorder, tends to increase in the universe. White holes, by their nature, decrease entropy, which contradicts this fundamental principle. Moreover, the stability of white holes is a controversial issue. Some theories suggest that if they did form, they'd be extremely unstable and would probably collapse almost instantaneously into black holes. In outer space, white holes represent one of the most enigmatic and paradoxical concepts. These mirror images of black holes have characteristics that challenge our traditional understanding of physics. Let us understand in more detail what is the concept of a white hole in theoretical physics. At the heart of a white hole is its event horizon, a boundary not of inescapability, as it is with black holes, but of impenetrability. This event horizon marks the point where matter and energy are ejected, creating a spectacle of cosmic proportions. Unlike a black hole, which takes over everything, a white hole is the source of the expulsion, the cosmic fountain from which matter and energy arise. One of the most intriguing aspects of white holes is the concept of time reversal. In the universe, time usually flows in one direction, from the past to the future. However, white holes seem to reverse this flow. It's like watching a space movie played backwards, where the usual rules of time and space are reversed. Deepening into the nature of white holes, we face a realm of paradoxes and problems. One of the most important is their connection with the previously mentioned entropy. According to the second principle of thermodynamics, entropy, or the measure of disorder, should always increase in a closed system. However, white holes seem to ignore this law, decreasing entropy and ejecting matter in an ordered state. This apparent violation of thermodynamic laws presents a serious problem for our understanding of physical processes in the universe. How can such an object as a white hole exist if it contradicts such a fundamental principle? Another paradox lies in the concept of the arrow of time. Where the universe moves inexorably forward in time, white holes suggest a scenario in which time can flow backward, at least from a certain point of view. This concept breaks not only our understanding of time, but also the very nature of causality in the universe. Let us summarize the characteristics of white holes, their event horizons, the expulsion of matter, and the concept of time reversal present a fascinating but paradoxical picture for theories that, while we're looking to solve these problems, white holes remain in the realm of theoretical physics. As we delve deeper into the mysteries of the cosmos, the concept of white holes invites us to rethink our understanding of the universe. These theoretical objects are not just surprising anomalies. They may have profound cosmological implications. Consider the Big Bang, the colossal explosion that marked the beginning of our universe. Some theorists suggest that this pivotal moment in cosmic history was not just a random explosion, but that the event may have been a white hole of unimaginable magnitude, an eruption of matter and energy that gave birth to the cosmos. This view offers a radical new interpretation of the origin of our universe, suggesting that white holes may play a role in cosmic genesis. Imagine a white hole not just as a theoretical construct, but as the very source of the creation of our universe. In this scenario, the Big Bang could be envisioned as a white hole of unfathomable scale, spewing out matter, energy, and space-time that subsequently evolved into the stars, galaxies, and planets we observe today. This view offers a radical rethinking of the Big Bang. Instead of an undefined singularity, we have a white hole, an entity defined by the laws of physics, albeit in a form that stretches our understanding to its limits. This white hole may have been the first spark that set the stage for subsequent cosmic evolution. If the Big Bang was indeed a white hole, it raises profound questions about the nature of our universe. What was the source of this white hole? Was it the result of a collapse of the universe from another dimension, or the result of processes beyond our current scientific understanding? This concept also changes our perception of time and causality. If the Big Bang was a white hole, it suggests the existence of a universe with a more complex timeline, in which the beginning and end of cosmic phenomena are intertwined in ways we've yet to understand. This idea of the Big Bang as a white hole organically combines with the Big Bounce theory, according to which the beginning of our universe may be the result of the collapse of the previous universe. It unites the idea of cyclical universes, suggesting that each cosmic end can give rise to a new beginning, similar to the explosive genesis of a white hole. The existence of white holes may also confirm the concept of parallel universes. If white holes can eject matter and energy, could they be a gateway to other universes? This possibility is related to the multiverse theory, which postulates the existence of multiple, possibly infinite universes, along with our own. In parallel universes, there may be different versions of physics, alternate histories, and perhaps even variations of ourselves. Another intriguing connection relates to wormholes, hypothetical tunnels in space-time. Theoretical models suggest that wormholes could link distant regions of space, and perhaps even different universes. If white holes are connected to wormholes, they could serve as cosmic portals, opening paths to remote corners of the universe or other dimensions altogether. This connection raises tantalizing questions about the nature of space and time. Could white holes and wormholes allow travel over vast cosmic distances, or even between different universes? Looking into the future of astrophysics, we see that at the moment there's a lot of scientific research in one way or another affecting the subject of white holes. But two research papers stand out among the rest, shedding light on the mysterious nature of these cosmic objects and offering new ideas and possibilities that could revolutionize our understanding of white holes. The first paper takes us on a journey to the very edge of black and white holes. exploring the close connections between them and refocusing on the physics occurring near their horizons. The authors introduce the concept of horizon-penetrating coordinate systems, a revolutionary approach that allows us to distinguish between the horizons of black and white holes. They differ from standard curvature coordinates in a small near-horizon region to emphasize the distinction between black and white horizons, which depends on near-horizon physics. This study suggests that black holes may not be the cosmic dead ends we once thought. Instead, they may be in quantum superposition with white holes, creating a scenario in which observed phenomena may hint at the existence of these theoretical white counterparts. The paper also delves into the role of quantum physics in these near-horizon regions, suggesting that quantum effects may dominate, leading to significant implications for our understanding of white holes. However, the authors emphasize that there's a problem in observational astrophysics, in which there is substantial observational evidence for black holes, but relatively weak observational support for white holes. Moving on to the second paper, titled New Black-to-White Hole Solutions with Improved Geometry and Energy Conditions, we find that the focus here is on the way to convert black holes into white holes, guided by the principles of quantum gravity. This study presents models in which the effects of quantum gravity prevent the formation of singularities inside black holes, providing a smooth transition to white holes. This solves the long-standing paradox of information loss by assuming that matter can pass through a black hole and appear in a white hole. The paper also explores geodesics within these models, confirming the completeness of particle trajectories in the transition from the black hole region to the white hole region. This supports the idea of a continuous, unimpeded flow of matter, changing our understanding of these cosmic phenomena. By integrating these theoretical developments with emerging technologies, we stand on the threshold of a new era in astrophysics. The future of white hole research promises to reveal new aspects of the universe, where the boundaries between quantum mechanics and general relativity are blurring. To summarize, we can say that the future of white hole research is very bright. Who knows? Perhaps very soon, we'll be able to discover indirect evidence for the existence of these intriguing objects. There is a hidden order in the void of space, a subtle force that controls the movements of the celestial bodies with an invisible hand. Far from the chaotic randomness one might expect in the vast cosmos, there is a mysterious harmony, a set of invisible rules that dictate the paths of planets, moons, and asteroids with remarkable precision. Consider for a moment that the giants of our solar system are not just isolated spheres of rock and gas, but participants in a grand gravitational party whose every move is influenced by the forces generated by their cosmic neighbors. Among the actors are Jupiter and its moons. Behind them also lies the asteroid belt, a vast ring of debris that holds voids of mysterious origin. These voids, devoid of the rocky features typically found in the rest of the belt, hint at an unseen participant silently shaping the structure of this cosmic phenomenon. Even distant Neptune and Pluto tell a tale of complex gravitational interaction, locked in such a precise rhythm that their paths never cross. These patterns and rhythms are constantly emerging in the vastness of space, hinting at the underlying order that governs the universe. Orbital resonance is the very concept behind this behavior. What forces act on this mechanism of behavior, both simple and bewilderingly complex at the same time? Let's find out. Behind the facade of the night sky, a complex network of forces operates to dictate the movements of celestial bodies. Gravity, the fundamental force that keeps our feet on Earth, extends far beyond our planet, creating the architecture of the cosmos on a grand scale. At the center of our solar system is the Sun, a colossal furnace of nuclear energy whose gravitational pull subordinates the motions of the planets around it. This gravitational interaction is not a one-way street. Each planet, in turn, exerts its own gravitational pull, creating a complex network of forces that affect their orbits. When two celestial bodies come close together, their gravitational fields interact, influencing each other as if playing a cosmic tug-of-war. This interaction can lead to subtle changes in their trajectories, an effect that's most pronounced in systems with closely rotating bodies, such as Jupiter and its Galilean moons. Consider the case of Jupiter, a giant of the solar system whose massive gravitational field holds a retinue of moons. Among them, the Galilean moons, Io, Europa, and Ganymede, exhibit a remarkable phenomenon known as mean motion resonance. This occurs when the periods of their orbits around Jupiter maintain a constant ratio, a delicate balance that prevents their trajectories from becoming chaotic, despite their close proximity. This gravitational interaction leads to a rhythmic alignment of the moons that repeats over time, ensuring their long-term stability. The forces at work do not simply pull the moons along their trajectories, but push them to positions that minimize potential disruptions to their orbits. Beyond the region of Jupiter and its moons, the gravitational interaction extends to the asteroid belt and beyond, where countless rocky bodies are influenced by the gravitational pull of nearby planets. This interaction can lead to gaps in the asteroid belt, regions devoid of asteroids formed by the resonant effects of Jupiter's gravity. Based on the above, we can conclude that gravity acts as a weaver in the cosmos. Its threads pull and shape the trajectories of celestial bodies, creating a harmonious order out of potential chaos. This gravitational influence, a fundamental aspect of the universe, provides the basis for the interaction of planets, moons, and stars. But is it as easy to understand as it is obvious? In the gravitational embrace of Jupiter, the largest planet in our solar system, there is an amazing example of cosmic harmony, the Laplace resonance. This unique gravitational relationship involves the three previously mentioned major moons of Jupiter, Io, Europa, and Ganymede. Each of these moons, a wondrous world, is involved in a synchronous orbital interaction that has intrigued scientists for centuries. Laplace resonance is characterized by the exact ratio of the orbital periods of these moons. For every 4 orbits that Io completes, Europa orbits twice, and Ganymede completes 1 orbit. Due to this gravitational pattern, the moons align at regular intervals in a pattern that repeats itself every 7 Earth days. Resonance is not just a curious phenomenon. It has profound implications for the moons themselves. Gravitational interactions, especially between Io and Europa, cause significant tidal heating on Io, which promotes volcanic activity. This energy dissipation also affects Europa, potentially contributing to the maintenance of its subsurface ocean. Laplace resonance provides a clear example of how celestial bodies, through mutual gravitational influence, can establish stable and predictable patterns that persist over centuries. But the story doesn't end with satellites alone. Saturn, the jewel of our solar system, is surrounded by a series of mysterious rings. These rings are made up of countless particles of ice and rock, from a speck of dust to a mountain-sized lump. And yet, among this continuously glowing belt are gaps, vast stretches of emptiness that baffle. What had to happen for them to occur? One of these discontinuities, the Cassini separation, is evidence of the forces of orbital resonance. It's not simply a lack of material, but a boundary created by the gravitational influence of Saturn's moon, Mimas. Mimas's role in creating this gap is a fascinating example of orbital resonance in action. Mimas, although small compared to the gas giant around which it orbits, exerts a significant periodic gravitational influence on the particles inside the rings. This effect is not random. It occurs at specific points in the orbits of the particles, because their orbital periods are in resonance with the orbit of Mimas. For every 2 orbits that Mimas makes, the particles at the edge of the ring make 1, thus having a resonance in the ratio 2:1, which leads to repeated gravitational interactions at the same point of the particles' orbits. These repeated interactions have a cumulative effect and act like a cosmic broom, clearing the way and creating the Cassini separation. Particles that once occupied this space were either pushed into new orbits or stuck together to form larger bodies, leaving behind the void that marks the boundary between Saturn's A and B rings. This process is akin to nudging a seesaw at just the right moments. Each nudge adds a little more energy to the system, and in the case of the planet's rings, each gravitational push by Mimas moves the particles around, clearing a path in the rings. However, the influence of Mimas and orbital resonance is not limited to the Cassini separation. Similar resonances caused by Saturn's other moons shape the complex structures of the rings, creating a pattern of discontinuities and dense bands that make the planet's rings dynamic and ever-changing. Between the orbits of Mars and Jupiter lies the asteroid belt, a huge cluster of rocky remnants from the era of the formation of the solar system. However, this region is unevenly filled. There are distinct gaps known as Kirkwood gaps. These gaps are not the result of missing asteroids, but represent areas where Jupiter's gravitational influence has organized stellar clearing. Kirkwood gaps are named after Daniel Kirkwood, who observed in the 19th century that these gaps correspond to orbital resonances with Jupiter. In these resonances, the orbital period of the asteroid in the gap will have a simple ratio to Jupiter's orbital period, such as 1 to 2, 2 to 3, or 3 to 4. At such distances from the Sun, the asteroid's orbit will periodically align with Jupiter in a pattern that will be repeated at each orbit. Over time, these repeated alignments expose the asteroid to regular gravitational jolts from Jupiter, changing its orbit. When an asteroid falls into one of these resonance gaps, repeated gravitational jolts from Jupiter can increase the eccentricity of the asteroid's orbit, putting it on a more elliptical trajectory. This could cause the asteroid to move to a different orbit, leaving the resonance gap-free. To visualize this phenomenon, imagine an asteroid approaching one of these resonant orbits. As it approaches, Jupiter's gravitational pull synchronizes with the asteroid's orbit. If this synchronization falls within the Kirkwood gap, the asteroid experiences repeated pulls, pulling up slightly each time it completes its orbit. Eventually, these jolts can shift the asteroid's orbit, pushing it out of the resonance gap into a less perturbed region, where Jupiter's influence is less synchronized with its orbit. In the outer part of our solar system, beyond the gas giants and the icy Kuiper belt, lies another fascinating story of celestial harmony. Neptune, the 8th planet from the Sun, and Pluto, a dwarf planet in our system that was once considered the 9th, have a unique gravitational relationship that defies the odds of collision. This relationship is determined by the 3-to-2 resonance gravitational lock, which ensures that for every 3 revolutions of Neptune around the Sun, there are 2 revolutions of Pluto. This rhythmic interaction is not just a coincidence. The influence of this resonance is profound, shaping their orbital trajectory so that, despite their overlapping orbits, Neptune and Pluto never collide. Pluto's orbit, influenced by this resonance, is markedly eccentric and tilted as it winds above and below the plane of the solar system, balancing over millennia. This harmonious arrangement emphasizes the complex laws of physics that ensure stability and order in the vastness of space. But what do all these things have in common? The satellites, the planets themselves, their rings and asteroid belts. And why are only some of them affected by orbital resonance? The answer lies in the subtle interplay of celestial mechanics, where eccentricity, inclination, and gravitational forces come together. Orbital resonance is based on 3 key factors: eccentricity, a measure of the elongation of an orbit; inclination, the tilt of an orbit relative to a reference plane, whether concerning a star or another celestial body; and gravitational forces, which tie everything together. These elements are intertwined, determining whether a body falls into the grip of orbital resonance or avoids it. When a celestial body falls into resonance, its orbit becomes locked in a gravitational interaction with another body, usually a much larger one. This fixation can increase stability, as seen with Neptune and Pluto. However, there are simultaneous exceptions in which objects will be ejected from their trajectories, cutting gaps in regions such as the asteroid belt. The role of eccentricity and tilt in this process cannot be underestimated. A small increase in eccentricity, for example, can dramatically change the gravitational interaction of a body, bringing it into or out of resonance. Similarly, inclination can tilt an orbit so that it interacts with the gravitational influence of another body at just the right point to enter resonance. This complex balance of forces makes orbital resonance a selective phenomenon, affecting only those bodies that meet the precise conditions necessary to synchronize with the rhythm of their larger neighbors. It's a cosmic lottery where the prize is a stable orbit or, in some cases, total expulsion from the system. Looking beyond our solar system, we discover how the action of orbital resonance plays out on a grand cosmic stage, determining the fate of exoplanetary systems across the universe. These distant systems, with their unique clusters of planets, offer a fascinating glimpse into the complex design of the celestial mechanics that govern them. Observations of these distant worlds have revealed cases where the planets keep pace with each other, their orbital periods maintaining an exact relationship. One striking example is the TRAPPIST-1 system, where several Earth-sized planets are locked in a complex chain of resonances. Such configurations raise intriguing questions about the formation and evolution of planetary systems, challenging and refining our theories. Meanwhile, the major planets of the solar system themselves do not show a clear pattern of orbital resonance with each other. Their orbital periods don't have a simple integer ratio that would indicate resonance. While there are close resonances, such as the 5:2 resonance between Jupiter and Saturn, they're not as precise or stable as resonances between some moons, or in more dynamically bound systems such as Pluto and Neptune. The implications of these observations go far beyond simply cataloging celestial phenomena. They provide insight into the processes governing planet formation and suggest that resonances may play a key role in the assembly of planetary systems from protoplanetary disks orbiting young stars. As we continue to observe and study such phenomena, each new study peels away another layer, revealing the intricate plan of the universe, bringing us closer to unraveling the fundamental principles that govern celestial motion and illuminating the very essence of our existence.